Awesome. Hello, everybody. My name is Kevin Kawchak. I'm the founder CEO of ChemicalQDevice, here for developer transition, machine learning to quantum machine learning. This is July 26, 2023, number 93. And so I have more people coming in, lots of people from different platforms here. So the biggest thing is it's really not that bad, right? If you want to insert quantum circuits, quantum algorithms into existing deep learning neural networks, number one, play with the models. So I would say some key ones definitely are Pennylane, qiskit. You definitely have Google Cirq, TensorFlow Quantum, Torch Quantum. And they'll have the framework set up. So you could read a little bit about quantum and then start to optimize those algorithms. So that is definitely recommended there. So I'm going to start off with just that. So the current landscape for quantum machine learning. And so you can see in the chat there. And so basically PyTorch and TensorFlow, I put this in the chat, are the two leaders, for machine learning, deep learning. And if you come across different models across the web, chances are they're likely going to be one of those two. Now, they started to get big around 2012, I think, for TensorFlow. They had an update in 2015. So it's very much a classical world that we live in with a lot of this. And same thing with PyTorch. I think PyTorch is actually coming on a little bit stronger as of recently. And I don't know how the metric is, if it's just, number of notebooks, those types of things. But when you think of coding and you think of machine learning, you're typically going to mention one of those two. So you have PyTorch, TensorFlow. Now, keras is also part of TensorFlow, or it's not part of, but it's associated with. And then keras makes things even easier to do. Some would say more so for beginners. And then the Hugging Face is an interesting organization. They do a lot of hybrid models. So if you go onto and I put the link in there too, the Hugging Face models, you'll have a lot of times like a vision transformer. These are all classical. You'll have some chat GPT component to it. And, these are leaderboards, competitions, fighting over the best, top 1, top 5 accuracy. Scikit-learn, you want to always check. And again, this is classical. If there's an existing algorithm and an existing method classically, always check classically first, before starting to get into quantum, even though you'll be developing with quantum and you might not get the results till a little bit later on. And Spark is more for this last one, Apache Spark, and this corresponds to the, the slide for this week, is if you need to split up the complexity of data sets in the cloud, that's what Apache Spark is good for. So at the end of each of these sections, I'll have questions. So the trend and basically what's going to be happening is that all of this, certain components, you'll find a quantum algorithm that you want to try, and things will start to really get, Pennylane does an awesome job with this, by the way, models, this specific quantum circuit is we're getting better and better and proving how to use it and the results for it. So if you're brand new to quantum computing, I'm putting in the chat here Meetups. So there's other Meetups too, but these are the ones that I find are meeting more frequently. So the first one's Quantum Computing with Anna. So she has a medical background. She's a physicist as well. So you'll see a lot of these kind of the quantum gates and quantum circuits. It's really hard to get into quantum computing if you're not part of a group, right? Or don't attend any other types of sessions, those types of things. Now, the second one I put in there, Washington Quantum Computing Meetup, that one's really helpful as well. They're associated with Toronto Meetup. And basically, they have a lot of guest speakers, a lot of people that are really kind of thorough in their specific areas in quantum computing, quantum machine learning. Physics with Friends is very interesting. It covers, depending on the event, so the week basically, you'll have quantum mechanics, you'll have quantum computing. If Jenny will get into specific areas of all of these as well. And the last one is mine, so quantum computing and healthcare discussion. So these are all up on Meetup right there. So for everybody to see. Are there any questions at this point? Any questions regarding quantum machine learning, deep learning, this transition that a lot of people are going to be taking? And feel free, so you can unmute or you can come on as well. I'd be interested to hear at one point, basically how would it help you in this background I'm going to share here as well. So the next one is basically there are several different platforms out there. So for quantum computing, and Quantinuum, which is based on Honeywell, so the Fortune 100 company, is called Tket. So it's Tket, and their claim to fame in the hardware end of it, so the quantum computer, is a technology called ion trap. So ion trap technology, and Tket has the service that allows you to optimize from different levels, ranging from 0, 1, and 2. Basically how fine-tuned do you want your quantum algorithm to try to get a speed up, these specific things. So these 3 links that I'm sharing with Quantinuum are basically different models. One's a video. I would definitely watch the video if you really want to program in quantum computing. Very helpful with Kathrin Spendier at this is a Womanium Quantum, their Slack channel as well. So some of these Slack channels are just kind of getting going. I would say the Quantinuum is kind of gaining momentum. I would say I just posted in it today, and don't be afraid to ask simple questions. That's why other people like helping, and moderators like to help on anything from these Slack channels to Pennylane's specific things. And the next one, and we'll have a pause after the Microsoft, qsharp, and it's actually pretty well going. So they have these different events that they've been at, and pretty much all of these major platforms that are looking at releasing a quantum computer in the next 3 or 5 years are going to have some major their quantum machine learning initiatives with this. So I included, so GitHub is a great resource for a lot of these. And then another one is the YouTube videos. Just sit and watch, a lot of these experts learn, start to teach other people, develop code. It's a hard thing, but if you're completely involved with it, I think that you'll start to see the progress start to pan out. Are there any questions at this point? So I started basically talking about the machine learning, PyTorch, TensorFlow, Hugging Face. You have Keras. You have a number of these. You have Apache Spark. And it's kind of like the standard. So in order for quantum to work, in my opinion, is that these people from deep learning are going to have an intrigue to incorporate quantum computing and quantum code into their models. And the best thing we can do is try to get the best performance that we can with that. So if it's medical, finance, transportation, these types of things as well. And I saw a couple other people hop on here. So are there any questions at this point? So I've covered Quantinuum, Microsoft as well, and then some of the machine learning. So feel free, so you can either unmute or you can come on as well. And the next two is, people have different flavors of the ways that you can access quantum simulators and quantum computers. Now, if you're in the business world and you have everything worked out with AWS, so meaning monthly billing, it's a very elaborate thing to hop onto AWS. Sometimes they'll give you free credits. I put this in the chat, and they have their own notebooks that you could run as well. So you see advanced circuits, analog, it's called Hamiltonian simulation, hybrid quantum algorithms. And any questions regarding AWS? So a lot of people ask, is it Braket or is it Braket? And I see people that work for AWS and they call it Braket. The name itself, so it's Bra, and Ket is a notation in quantum mechanics. So you can see things, and they're most commonly, I think, written in the Ket notation. So that's Ket. And then the other one is Bra. So that's where that notation comes in. It is Braket for AWS. So we'll see. It'll just depend on if more people pretend to or want to call it Braket or Braket. Just one of those things. Now, Torch Quantum is interesting. They're kind of getting going. So Torch Quantum obviously would be like a PyTorch derivative. So if you're into ML, you know a ton about PyTorch typically. And they have this tutorial that helps. And similar to the Quantinuum developments is that a lot of this optimizing circuits. So it's basically how to make them run faster, lower number of complex gates. So you have less 2-qubit gates and more like a single qubit gate, like you'll see X gates or not gates in the place of these more complex gates. And I included also with that, so with the Torch Quantum, and again, towards the end, you can click on the triple dot to download the chat for these links and get going on models. Basically, is they also have a transformer model. So transformers are huge in today's classical, the Hugging Face, and now we start to see these appear on the quantum realm as well. And these next two, if you've been part of the discussion, are there any questions regarding Torch Quantum? And these next two, so you basically have Pennylane, which probably has the most models out there. They have pictures. I mean, you still have to know code, those types of things, but they usually work right away. So in my opinion, some of the other ones don't typically do that. So just make sure to do the pip install Pennylane, and you should be pretty good to go there. Now, this first one I'll highlight. So generalization in QML from few training data. Now, this is based on a paper. It's a Google paper. And I tried doing this last night. And it basically says that in quantum machine learning, if it's pure quantum, like I don't think this is for a hybrid model. So less of like, Torch and TensorFlow. It tends to be better off with quantum based on mathematical advantages and you don't need as much data compared to a classical model. So again, I tried doing this last night. The hybrid model I have is quantum transfer learning. I didn't find that, at least initially, but that's why you run these, right? You run the models and you're comparing against literature that you read, these types of things as well. Also, coming from the GANs, so generative adversarial networks, these are huge in classical, creating basically data out of nothing with a very minimal, like say 10 images and 90% noise, converting that noise into images that look like the 10 images. And then the Maria Schald, that's really helpful. She's a leader in this field and for Xanadu, for QML. Go ahead, Tim.
Oh, do you have any suggestions for a good online class to take for certification for quantum machine learning?
Yeah, there's two. I've taken two on edX. So edX is MIT based, and the first one, I'm trying to think of it's a Linux foundation, like Linux, and then foundation. So you could search for it by like quantum algorithms, Linux Foundation. It's for beginners. It's not as in depth, but it's very helpful if you don't know, the basics of, qiskit gates, those types of things. On that same platform, so on edX, there's also the one I would recommend to anybody as you get going with quantum. It's a little bit more advanced, and it's just quantum machine learning. It's by University of Toronto. And it's a little bit longer. So I audited both these. I just watched the videos. But it really helps because you can really have a lot of that one-on-one time with experts, that have published a lot and work a lot with quantum. And I know there's different ones in Qiskit that you can get if you're, solely focused on Qiskit. But yeah, there should be a fair amount of that out there. And like I said, most of the training that I do is on edX.
Okay. Okay, and the ones you mentioned, are they expensive?
No, to audit these is just watching videos, so you don't have to pay for the certificate.
Okay.
So it just depends on your preference. If you really want to nail it down, like I'm looking more in general just to see what's out there. So I would just, watch all the videos in a couple of days. And then the certificates can range in cost. And I think they actually range in the time of the year. That's what it seems like. I couldn't give you a definite, but I don't think they're too extraordinary.
Okay.
But you have to pass tests and those types of things.
All right.
Anybody else? So again, so starting with Qiskit here, so at the bottom of the chat here, Qiskit is great for beginners. If you haven't started programming a circuit, you can, I do stuff on Qiskit in the lab all the time. Some of it's, it just depends on what I'm working on, but you can run, and they just had an announcement today that they're upgrading the free tier, meaning that the older ones, like my 7-qubit Nairobi that I would always use, you're going higher in qubits, and assumingly probably better in noise. I don't know for sure. Those types of things. So as these progress, they're typically getting bigger in quantum computers. You can, look at the announcement. I think it was today it was made for Qiskit. They're finishing up summer school as well. You can look at the announcements and see the resources. Like the Qiskit is, this is free tier. I haven't had to pay anything. I can run notebooks and print them as a PDF and download them as a .ipynbs. So it's a really helpful service. So the ones that I put in here, these first two are both notebooks. So you'll see this. So a big Qiskit announcement was the torch connector. So meaning that you could do pytorch, this hybrid model with Qiskit and torch. So that's one of those as well. And the models are great because they give you an idea. Oh, okay, this is out there. This is possible. I can combine this with this. I just updated one from a default.qubit to lightning.qubit. So it made the whole thing a lot faster, probably 2 or 3 times on a previous model that I did. And the last one, the future of quantum machine learning, is great. So it's got 4 or 5 experts on it. So, Maria Schald, it's got, let's see, I think a gentleman from Microsoft, R.M. Haro from MIT. But I would watch that like today, and then in a couple months go back to it and see how much you learned along the way, right? Because for me, it was really challenging, watching these types of videos up front. And I'll go back and I can actually I follow a lot more accurately what they're saying. So I think it's only an hour. It's a Qiskit video, but I would definitely recommend that one. And then kind of the Cirq stuff. And I'm really interested in what everybody's running these days, because Cirq is a great platform as well. They have some good notebooks. So Google's QSIM was the simulator that was used against the original quantum supremacy quantum computer, a gate-based superconducting qubit, back in October 19. And you and I have access to this QSIM simulator. It's not running on a supercomputer anymore. It's running on a 90-core Xeon processor, but that's pretty good. So to avoid the whole GPU, it's a jump to GPU with the code, like you have to change things in your notebook. The QSIM simulator that Google has is, I've got it to work a little bit in a bigger notebook, but it's something that's free. Not a lot of people know about it. So they also do things like calculate gradients workshop and barren plateaus. So those two in specific are more, optimizing your model, trying to get the best out of your circuit. Go ahead, Tim.
Oh, you mentioned that you're curious about, what people are using nowadays. I mainly focus on Qiskit, but then I've also learned Cirq, and then I'm also working on learning qsharp, and that's part of the way I am with computer stuff in general, is I try to learn different techniques, because not everything you don't have one certain technique, such as a language, that's going to work well for every single thing. So sometimes you gotta do different things, and that's one of the things I learned doing my PhD program was we had mainly 2 different packages for when we were doing molecular dynamics. We had charm and NAMD, and we used them both, and they both had their good and bad, and one of them worked well for some situations, and one worked well for another situation. And then also with the languages, Perl worked well for a lot of things, but then Python also worked well for a lot of things.
Yeah, I appreciate you bringing that up. I mean, there's multiple things that I don't know if you're talking about runtimes or performance, accuracy. A lot of times for me, it's more like the model. Like you find a really good model that, say, for instance, a quantum transfer learning model, it runs any high resolution image. The quantum component is not as big as the classical component, like a ResNet convolutional neural net. But yeah, these types of things, I wouldn't look at it like it's trying to confuse you. I think it's just there's many good options out there as far as like, I tried this, I'll try this, see what works better. Any other questions regarding this? So this could be, if you're working in PyTorch or TensorFlow right now, or even Hugging Face or Keras, and how can you make that jump to it? And a lot of times I don't know, it seems so easy now because I work on it all the time. But are there any questions regarding that, like just how to make that first step to press play in a hybrid model, classical quantum model? Okay, and then so this last part is about so I mostly was talking about front ends. So say for instance, like Quantinuum, their front end is basically like qiskit, and then in the middle, because they work with all these different platforms, is Tket or PyTicket, and then the back ends are the actual quantum computers or the simulators. So I just put it in the chat. The NVIDIA GPU, you have to pay for it, okay? I haven't come across a way not to pay for it. So the first three links, this NVIDIA QQuantum, are ways to get started. Now, I know you have to update your model once if you go to a single GPU quantum simulator. And I think you have to keep updating it if you keep adding more GPUs. So that would be multi-GPU. Now, the ones below it are the ones that are kind of a little bit, they're all CPUs. So it's basically simulating the physics of what we know about quantum computing inside of a CPU. So this is the QSIM I mentioned, which seems like try to get this to work. Like it looks awesome. Lightning.Cocos is Pennylane. And then the TN one is AWS Braket. It's a tensor network quantum simulator. So QSIM, I think they say up to 40 qubits, 40 quantum bits, which is pretty high for a simulator. And then TN1 safe is like 50 qubits max, or 50 quantum bits. So those should help out a lot. And then this last part here is basically, as you have time, you really want to, okay, so start to look at literature, and then also these, okay. What I think is coming up in quantum machine learning is this. So better understanding of dataset processing with the qubit physics. Okay, this is resonated through literature. It's not just me. More variational circuit parameters. So typically if you have a circuit like a rotational gate, you look at the theta angle, and it's version of deep learning. So deep learning has weights and biases. The variational circuit has theta values in these rotational gates. And there was a QBraid talk I included in there, and they said just that is, we're going to start to pick up as far as the in-depthness and likely results with it too. Also, different types of circuits. We're in this phase, these variational quantum algorithms or quantum circuits that a lot of us work with were meant for NISQ quantum computers. I think 2013 they were first developed, but figure more kind of like deep learning stuff, coming up in the years, and also improve pulse programming. So a good tactic seems to be start with gate models, meaning like a Hadamard gate or rotational gate or CNOTs, get it to work, and then switch over to pulse programming once you understand it, and then fine tune it from there. Because pulse programming is typically harder, but it gives you better control over the quantum bits. So that's a big thing there. And then I put a bunch of Google researchers. And then this last part here, one of the national labs is doing a great job. They're basically like, saying this is how barren plateaus, which are not desired in quantum computer, are made. And it can be because of more C0 gates or entanglement, more qubits, more global measurements instead of local measurements. But those are really good papers too. So I wanted to kind of step back here and then, kind of see, and where people are at, in their classical journey. If you're getting started with quantum machine learning, coming from non-classical machine learning, that's fine too. So any questions regarding the material? And then you can also put in the chat as well. So, and then Tim, did you have anything?
No, not right now.
So what else is going on is Womanium. So Womanium Quantum is it's a female-based organization that it's lots of YouTube videos, like I think 3 hours a day at its peak. And the Quantinuum link that I put in the chat is really good to get into Tket, Tket, which is this, their system, their ecosystem. And it's very flexible with other things like IBM's Qiskit and Xanadu's Pennylane as well. And I see a number of people returning. So Samuel or Carlos, go ahead. And then if not, we have some new people too. So Marcia or Sahil, be great to hear from you.
Sure. Hi.
Hi.
Thank you so much for the presentation. I am new to this field, so everything you're saying is interesting and phenomenal to me. So I don't really have questions.
Yeah, and like I said, don't be intimidated. You will have to learn it all. But like where I'm in the journey is, it just seems simple. Like you just have a notebook or a model that you found, Pennylane, Qiskit, and to just run it, improve it, incorporate new things into it. The hands-on aspect to it too. And there is a lot of learning and likely teaching involved too, because you have to read the papers. I'll also put an organization in here. Okay, so it's actually called QHack. So QHack is just what it sounds like, quantum hacking, but it's ethical. And they have a 2023 and a 2022, and they're phenomenal. So they have experts on, and they'll talk for an hour. Sometimes there'll be an interview, and it'll just be more about their these coders personal lives. And they have meme contests with quantum machine learning, and it's good, so they have bright colors. Beyond that, like the top experts in the field are on it too, from MIT, IBM, definitely Pennylane, definitely Google, definitely LANL, so Los Alamos National Laboratory as well. So I would check those out. And especially Marcia, the specific areas, there's like 40 or 50 per year. So scroll through the videos, and if you want to do like GANs, or if you want to do learn more about embeddings, quantum embeddings, it's the QHack. I pretty much watched all the ones I wanted to. I'm at like 35 or 40. But
Thank
very
you so
helpful.
much. I'm on the webpage and it's really excellent. Lots of good stuff.
Yeah, they spend a lot of time, and you'll hear some of so when LANL gets on, which is this national lab, and Google, they'll say, you guys do a great job. Like these things just don't happen. They purposefully spent their time to make this great quantum machine learning community.
Wow, thank you so much. Thanks for sharing.
Yeah, you're welcome. Anybody else that we haven't heard from? And if I called your name, you could come on. So Matthias or Jaidev?
Oh, hi, Kevin. It's
Yeah, go ahead.
Edwin. Yeah. It's interesting, the discussion, and yeah, myself, I'm still continuing with that paper. I think I mentioned a while some meeting ago. It's by Maria Schuld and Nathan. It's titled "Is Quantum Advantage the Right Goal for Quantum Machine Learning?" Well, the one of the questions, I think one of the concerns or something they raise in the paper is that is the difference between quantum and classical machine learning. You know, they're kind of pointing to the fact that uh, while 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 classical machine learning has become so good practically, and it's solving many problems and giving many answers, it's the models, these deep learning models are very difficult theoretically, while on the other hand, quantum itself is difficult to implement practically, while the theory is the one that's kind of guiding all the research.
Yeah.
Yeah.
Yeah, I appreciate you bringing that up. I mean, in some of mine, it's hard to get an apples to apples because I was fortunate enough I compared three classical, these are deep learning models. They're transfer learning to the quantum hybrid model. And, the quantum one that's the most similar to the classical only one, it's challenging because you have to try to get the parameters right, or more hyperparameters right, to get this, direct comparison. Now, a lot of times you can do other cool stuff if you're, not there yet with like saying I have quantum advantage now. And by that, I mean, just keep switching out the algorithms of the specific model, and you'll learn a lot from that too. So it's not just one thing. It's not like, to say you have quantum advantage is usually maybe on the algorithm, basis, and then you carry it into the implementation and into a model. But yeah, there's many things you can do that are very productive, even if you can't prove it 10 times that you had quantum advantage based on the algorithm, and now it's inserted into a model. So that's just one of the things you can do, is read a bunch of papers and use their algorithms too, and cite their sources, and then, test all of these different ones in your model as well. And again, that's the whole goal, is to get quantum advantage, but on the path to it. And so Jaidev said he's from Singapore, very early here. Okay, before tape break, yeah. Now, completely new to the field, am a mentor on AI and medicine at Deep Learning AI. Okay. And then I need to figure out more before I can contribute. And that's fine. I'm more interested in what everybody does, right? Because it's a huge step, because you're going to be devoting a lot of your time to it. So I've done a bunch of research in medical as well, and now I'm doing medical image analysis. And it's more about making the quantum aspect work, as opposed to just like, trying to do everything in medical. That's from my perspective right now. Meaning the quantum algorithm, so there's steps, right? So the quantum algorithm works. Okay, it works better. Okay, now we have a quantum algorithm that works better than the field. And then does the quantum algorithm work? Is it generalizable across different data sets? So it's called generalizability. You probably know this. So yeah, it's the steps that the whole industry is taking now, as far as like, okay, we have the algorithm, we tested it before we put in, and now it's kind of building up from that point. And then understanding the physics better. So, this rotational gate here at this time, and this alternating pattern of embedding versus rotation, or versus training layers, those types of things is the core of it, right? Because I can also take images that are non-medical, although all the data sets I'm typically testing are medical images. So I hope that helped, but it's basically, you're going to gain the fastest by running the models, right? Pennylane models, just click play. They run really well in Colab. You should even be able to run them in a Qiskit notebook too. So just download it, upload it to Qiskit, and then, you can also do a Qiskit backend, like a real quantum computer. So again, it's nothing to be really scared of, I would say, at all, because a lot of the hard work has been done. And then the fine tuning of it all, so say making your algorithm even better, that's really hard, like to go to that next step, because you're talking about many papers in literature, watching experts on QHack or, say Qiskit has these things as well too. But the worst thing to do is just nothing. And the best thing is to do something that's resembling what you're doing now, even if you don't fully understand it. So, yeah, so I appreciate the compliments here. And again, everything's on my end is going to be going more towards algorithms, better understanding the algorithm as it relates to that specific data set, and then better predicting the results of it all. And this is basically with literature helping things out on my end as well. But yeah, it's very cool because, and you could go back and tell everybody from, deeplearning.ai is that it's not as scary as it looks. It's just there's a lot of information out there. And I try to filter it down, say like, okay, just solely focus on models, right? Just run them, see what's different. So I'll give you an example, because this is something so Jaidev and other people could understand. So you have a deep learning neural network called ResNet, okay? So the one that you have is, say, ResNet 30, well, let's just say 18. Now the 18 ResNet outputs 512 elements. Now those 512 elements go into the quantum circuit. The dimensions get reduced, and then it's run in the quantum circuit. And at the end of that, the classical actually does the physical classification of the image classification model. So during that time in the quantum circuit, there's physics of the qubits, these simulated qubits in a CPU, this lightning.gpu, sorry, default.qubit or lightning.qubit simulator. And the data is moving in a different way than it's used to moving in a classical setup. So say, for instance, like if you have two classes of data, ultimately in a quantum bit, you want all of one class in a dot on one side of the quantum bit. And then on the exact opposite, you want all of the other class on a dot. And then in between that, you have linear separability. Okay. So that linear separability is, using quantum mechanics in a way that's that hasn't been done classically, as far as I know. So that's an example of a notebook. Is it's embedding classical data into quantum data. While it's in that quantum data, the data set's being moved in a certain way that is particular to quantum mechanics, quantum physics. Anybody else? So Tim, you could come back on, or Samuel.
This just an aside, Kevin. Yeah, but there's a certain paper that has been causing a lot of discussion on Twitter. I think since yesterday or something. It's in the area of quantum mechanics. Really, it's not really quantum computing, but yeah, I just felt that I should mention. Yeah, regarding something like superconducting at room temperature, something like that.
Oh yeah. I came across that too. I think that's more so to be used in a gate-based superconducting qubit, but it's room temperature. I saw that.
Oh, okay.
Awesome. Anybody else that just came on? So Ricky, we also haven't heard from Carlos or Matthias. Ricky, Carlos, Matthias.
Hey, how are you guys? My
Good,
name
how are
is
you?
Ricky. Good.
Did you have a specific question?
Oh, no. I'm just here to listen and learn.
Yeah. So
Thank
basically,
you.
we've gone from machine learning and then the topics into quantum machine learning. And then chances are it still might remain, TensorFlow and Torch, PyTorch. And my guess is they want to limit the number of packages to be installed. So say, for instance, like, if you're already doing PyTorch Hugging Face, That'd be PyTorch, Hugging Face, Pennylane. So there may be something like that, right? So I think a lot of it's just dependent on results, even simulated results with quantum simulators. But that the world between quantum and classical, based on financial investments and progress in papers, may be coming a closer, in time to come, for the benefit of simplicity too.
On the topic of the I think the match between quantum and quantum computing and classical machine learning. I think you mentioned something about comparing apples to apples, but in the paper I want to read and see whether they discuss some kind of complementarity, because like you always mention that it's where problems that are solved well by the classical side are not like ideal for quantum. It's really for where the classical side comes short. So I want to see whether they talk really about that complementarity.
Yeah, I mean, in these types of things, I was on this qiskit presentation, and they said there's 3 different ways. It was like a 2-part. It's their 2021 summer school. You either have an algorithm, a quantum algorithm that you can just add parameters and optimize those types of things, or like you have a classical algorithm that's no good, and then you have a quantum algorithm that's better than it, or you could base it all on its efficiency of processing a specific data set. So, there's that kind of stuff. Now, when I say apples to apples or apples to oranges, apples to apples, it's hard to do, because say if you have strictly like a PyTorch, deep learning, transfer learning, these types of things, there are certain terms, like I think it was momentum that, and the quantum notebook, there wasn't. And effectively, it's really hard. So you're not going to beat classical usually on a quantum simulator, because it tends to run slower. But on the performance end, if your loss is lower, your accuracy is higher, then you may have be in that range of having a quantum advantage. Now, to prove it, you're very likely going to have to prove that the algorithm itself, and you probably should start there, is there's a mathematical basis for it being better. Most of the efforts are being done to prove a speed up, but without the correct hardware, because it's too noisy, most of it is, if not all of it, that most people are going over after performance gains, like on the model, like the metrics of the, accuracy, loss, those types of things. But figure it's something that'll likely even be getting better, because when I saw the Quantinuum presentation and just the amount, like it take a regular qiskit circuit and just reduce it pretty well, as far as like the number of gates and likely how fast it would run, those types of things. It's compiled it basically into something that was more tangible or feasible. That there's likely other things, and especially the Torch Quantum group. So they're in MIT, the hand lab. Their stuff is very detailed. So they're on GitHub as well, as far as like, okay, let's get the very best quantum algorithm. But there's packages out there too, even classic with a Q at the end. They do a broad range of algorithms, but they'll compare something like for ion trap versus a gate-based superconducting qubit circuit, and it's way smaller than say IonQ versus the IBM or Google Braket. So yeah, I would say better stuff's coming up, and I kind of alluded to that, like pulse programming. We're still in mostly gate-based in mode right now, so H gates and X gates, but there's issues with the flexibility of it all, and yeah, it should be getting better for sure. Anybody else? I saw some another person come on. and feel free to put in the chat here. So Samuel had asked, the case of use for QML today. It's basically, after researching all these papers and doing my own, you're really trying to get the best algorithm possible for the best potential, accuracies. And there's different things like expressibility, entanglement capacity, like these are metrics placed on an algorithm testing it. In one case, high entanglement capacity really hurts the whole thing. It really slows it down. Another case, expressibility really helps with this specific case. So I would say it's just that. Like I've done 44 classes, and this is for 4,400 brain images. So this is really pushing it as far as the number of data, the number of classes. And I'd say my comparison to the classical model is good, but it's still, I need to address things even better, right? So as far as ready to ship a product yet, I'd say it's still kind of like, is the algorithm awesome? Do you fully understand it as well?
Kevin, I think previously you've talked about the applications, D-Wave and the applications of quantum in optimization. But could you talk of the instances in simulation?
Well, are you talking simulators?
Yeah, not like quantum being used to simulate maybe something in the real world. Yeah.
Yeah, I mostly use simulators, and this is for a specific VQA or variational quantum algorithm. Say for image classification, it's like right in the middle of all of this. So I believe Edwin's saying, so there's chemistry fit simulations, and there's you can simulate many things. There's a company called Boson Q Psi. They have a lot of steam right now, and basically they simulate different like aircraft parts or car parts using different aspects of quantum technologies. I don't know if they use annealing. So they might use QSIM. They did say supercompute. Well, QSIM's 90 cores. So yes, there's a fair amount of companies that are doing this. So typically it's not a full out thing. I know Polaris QB just does dimension reduction as opposed to like a full out simulation of molecules or peptides or different parts of the different aspects of chemistry. So yeah, I would check out those companies. So Boson Q Psi, PSI at the end, Polaris QB. Both of their members have talked on this panel, and without knowing 100% what other companies are doing, I would say that's probably the case. Is even to simulate H2, so hydrogen-hydrogen bond, that takes up this really big entangling circuit. I mean, relative to what you'd see in literature. So figure maybe more so on the approximation side as opposed to like full simulations of something that needs to be solved today that classically can't do.
Okay, thank you. I think I'll check them out.
Yeah, any other questions? So, it's okay if you're not in quantum 100%. I think it's definitely a possibility where your boss asks you, do you have quantum programming skills? I think that's in mainstream jobs, not like the companies that specialize it, although there are a fair number. So definitely good to have something in your resume as well. Okay, so generative asks a good visual style. I've created slides like this. So at the top, it's similar to AI. So AI, you have machine learning. Underneath machine learning, you have deep learning. So deep learning just has more layers than machine learning, for these specific tasks. So yes, you would have quantum computing at the top, and then they say 90% of quantum computing is quantum machine learning. So that's the big aspect of that. Now, you might also be asking how exactly are algorithms being inserted into different machine learning models? And it just depends. So there's quantum support vector machines. So if you have an SVM, now you have a QSVM, okay? But a certain aspect of is quantum. Now, if you have a principal component analysis, you now have a qPCA, okay? And you have clustering. So I think it's a QK means, something like that. And then obviously now so the trainable part of the deep learning neural network, like a ResNet, are the weights and the biases, like with neurons. Now, the trainable part with the quantum circuit are the parameters or rotation angles of these specific gates, Rx, Ry, Rz. So they're updated over time, separate from, the classical deep learning network. And that's the learning aspect of the parameterized quantum circuit / variational quantum algorithm. It has multiple names. So yes, they're used in different ways, but usually there's a quantum equivalent in machine learning to quantum machine learning, right? And I would say other researchers, and Salvador was on this panel, Salvador Andreas Vineka, he does image processing with quantum. So it's using qubits to process an image from raw data, say into a pixel, okay? So he wrote a book on this as well, quantum image processing. It's pretty close to what the title is. So yeah, it just depends, but you're dealing with qubits with quantum or bits with classical. Now, in order to simulate a quantum computer in a simulator, you have to use bits, and those bits make up qubits. And that process is not efficient. It uses a lot of RAM. So, but it's noise free. So that's a quantum simulator. Okay, so Seth Lloyd wrote a paper on this, on even back to Richard P. Feynman, Seth Lloyd. Richard Feynman had an experiment on a quantum simulator, not a real quantum computer, to see if you can even do quantum mechanics. And then Seth Lloyd later improved the whole thing. And then, now I can switch out like 5 different quantum simulators with no hassle. So, okay, yeah, more good questions too. Are general info abstractions patterns on pipelines across Q and M? And for you, Jaidev, coming from this background, I would check out, I posted, and for everybody, you could download the PDF for what was posted in the chat. It's called Developer Transitioning, from machine learning to QML. So download that and then start reading the LANO papers. So it stands for Los Alamos National Laboratory. And I could read that even back when I wasn't that experienced with QML, and I've since reread it, at least one more time. And that'll give you a good idea as far as these types of things. So, the info abstraction patterns on pipelines across Q, if it works at all. But yeah, there's many things you just have to find out kind of on your own, because you'll watch a lot of expert videos, you'll read a lot of papers, you'll attend discussions like this too, things like that. So, and there was another question here too. So was it deeplearning.ai that I saw challenged the usefulness of PCA in their newsletter? So that might be a question for Jaidev as well. But yeah, you're welcome for sure. And it's good to have these discussions because, as you heard me say before, it's the deep learning and machine learning community that will usher in, quantum machine learning, because the notebooks are written in classical. The bulk of the code, even today, will stay classical. And we're inserting a quantum algorithm here where it makes sense. So it's going to remain a classical world, meaning that to get these hybrid models up and running, like good ones, for some time. And just with anything, I mean, on the medical end, there's this thing called radiomics, which is basically treating AI with existing medical images. And I don't think it's clinical yet, so it's still research and development. And it's similar to what's going on with quantum machine learning is, you still do the research and development, because when it comes time and you hear some other research group figured it out, it might be too late, right? So that's why we do it R&D. Awesome. Anybody else we haven't heard from? You can come on again. So Tim or Marcia. Go ahead, Tim.
I was just going to make a remark that quantum computer is a misnomer because it's not a computer that runs on its own. It actually has a classical computer running it. So it'd be more aptly named a quantum processor. So it'd be similar to like a GPU, where you have your regular computer, and then for certain calculations that you want done quickly, or whatever certain things you want done quickly, you could use your specifically GPU for.
Yeah, I mean, they do call it, so quantum processing unit is a QPU. But yeah, in order to run a quantum computer, you need classical computers. So that's the thing. And it reminds me of this book. So it's Chris, or Worley's book, William Hurley's. So it's quantum computing for babies. And it goes through and it says, basically, it's for the really big problems. So if we had, this 1,000-qubit, real hardware with no noise, that would solve a lot of problems, right? So what we have today, we might have 30, 40 qubits simulated slower. And then we have say a Rigetti 80 qubit, real quantum computer, but it has way too much noise, right? So yeah, it's one of those things, but I think the crux of it is it's just like, honing any other skill you have is you do R&D on it before the really awesome stuff happens. So you have your, say, an Eagle 127 qubit algorithm, and all of a sudden they replace or bump it up, and now you can run it on a less noisy quantum circuit with a product where somewhere it makes sense, and say it's not sensitive like patient data, like you could use a quantum simulator for. But yeah, it's a hybrid model. So once you have like optimizers and you have loss functions, and in classical world, other people here probably know, is that these still apply. So say, for instance, if you have too much complexity, so the quantum and the classical part are, it's causing too much overfitting or undesirable overfitting. It's a hybrid model. So it's not like they're in a vacuum. And sometimes you can't just insert a quantum circuit and it just makes everything better. So that's where the physics behind it and understanding data sets and, how exactly, what's happening to every one of these images going through. It's probably something that'll be coming up. So you just design the best algorithm now. But, it's a lot of R&D. Awesome. So we still have some people on here we haven't heard from, and feel free to come on. And there's no wrong question. So you could ask, if you're not into regular machine learning, you want to jump straight into quantum machine learning. In certain cases, you can do that. You can run models, but to make them a lot better or to gain a lot more understanding, you likely have to read classical machine learning too. So don't throw out the fact that you have a strong machine learning or deep learning background, because now, that's the bulk of the notebooks, right? So I don't know if you caught the example I gave before. So the 512 elements coming off of ResNet 18 into a quantum circuit, this algorithm, process it, and then, it gets converted back into classical information. So bits, zeros and ones. And then another step, in my case, it was a classical classification. So yeah, and I would convey that too to other people, is basically like the harder part is understanding the model as a whole, And yes, there's intricacies in physics and qubits or qtrits or q-quarts, going up the ladder, that you're closer than you think you are, I would say. And especially it gets some good Pennylane models and qiskit models too. Yeah, so and then follow other leaders too. So Seth Lloyd, he speaks a lot on QPCAs. So Pennylane, a lot of these papers are like, I can't fully understand the math, even though I have a math minor. But Maria Schold, a lot of her more recent papers, the past 3 years, on how exactly like the embedding layer between classical to quantum, getting the best algorithms, those types of things. There's pretty much every big company has an expert they go to. Microsoft has one. There's, you could think of anything. Like even within Pennylane, there's multiple experts. So, and don't be afraid to post. So go to QSlacks. So you can go on QSlack channels for sure. GitHub, those types of things, find notebooks, run them. But a lot of times people are like, oh yeah, but the hardest part is just to click play on the notebook. I would start with the Pennylane, see if they run. If they don't, pip install Pennylane, and that usually fixes it. But you would be amazed how much you learn by just running some notebooks. Awesome. Any other last questions? Appreciate everybody coming on, even, if it's harder during the middle of the night too. So feel free to contact, during the week if you have any questions as well. So, and again, so you could download the chat notes with the triple dot. And then I also put the PDF. The thing that's resonating with me is the upcoming quantum machine learning, better understanding of data set processing. This is all within realm of what researchers are capable of doing. More parameters for the algorithms, different types of circuits, and pulse programming as well there too. Awesome. So thanks everybody for coming on. This has been discussion 93, developer transition, machine learning to quantum machine learning, July 26, 2023. Have a productive night and a good rest of the week. Take care, everybody.
All right. Thanks, Kevin.
Thanks, everybody.
Thank you,
Dr.
guys.
Kevin. Thank you.